I saw some problems arising from two participants. That is, they have successfully installed the software into their computer. The problem is when they run the software, when the test, they found they can't even go through all 5 tests because the SPP, they got some information like no session time here. You can see my screen here is quite small fonts, but you can see an error process single day, no session time. This is because the SPP failed. You can see here, the execution failed here. There is a label at the end of this command line. I checked this with Jonathan. He found this issue a few days ago, and we communicated several times on how to resolve this problem because I don't have his computer, and he returned me some information got from his screen. Unfortunately, we haven't figured out what's the source of the problem. I believe it's because the SPP program is quite different from the rest of the program. I let Jonathan try to run the other commands of the software. For example, the SP3 warp to generate warbits. It works. That command works. That means the SPP is quite something weird happened to SPP. SPP is quite independent in the software architecture because it's written using some advanced G-Fortran characteristics. So in this case, some system may not accommodate such characteristics of SPP. So I needed to, I guess it is because from our computers, we tried a lot of computers, a lot of systems like the Linux systems, Ubuntu, Red Hat, and some other system like SUSE and Mac. We didn't find any issues like this for SPP. So I can only guess it's because the advanced features are embedded into SPP programming. So I needed to ask my PhD to rewrite SPP using some basic features of Fortran language to avoid some advanced characteristics. And this is the usual strategy we wrote the other modules of the software, such as the list squares and residual editing and TEDit. For those modules, we use very simple grammar, Fortran grammar to finish the work. But for SPP, it's quite different. So I think it may be because of that. Let's see. So just in a few weeks, we can update you a new version of SPP. If you have the problem for SPP, then we can try. We can keep communication to see whether we can go through this problem for SPP to help you to run this software successfully. But at first, if you still have this problem, you can try to use some other computers like Linux system. I think Linux system is more flexible compared to Mac. Sometimes you can see very strange problems on Mac. In China we don't use Mac system actually. I'm the only person in my department to use Mac system. So we would like to use Windows or Linux system, and the Linux system is quite flexible in accommodating all different kinds of features of the programming languages. But the Mac sometimes is quite annoying. You can see it doesn't have many tools to be installed on this original, on this first installation. So you have to add a lot of tools on it to enable your programming, to enable the software to work. So this is, so sometimes you have to make some sacrifice on how to do the programming on Mac. All right. This is my explanation for some problem because I thought it was only Jonathan have this problem, but I believe some of you may have this problem as well because in nature have this issue as well. He reported this to me this morning. But at present, we don't have any method to break this issue. We don't know how to do it, how to solve this problem, because we cannot replay this problem in our computer. We tried the G14 version of yours, but we didn't have this problem. But you have in your Mac. So I don't understand what's the issue exactly is. All right, I can see here. Glad it's only for me. Glad it's not only for me. All right. Okay. Okay, I think we have 25 people now. So let's. So okay. Good morning again to everybody from Wuhan City, and this is a very good day today. And in Wuhan, we have very good sunshine, and hope you have it as well. Even if you are in the evening, you can have a good dinner after this this course. This is the second part of the course. So I'd like to introduce some advanced features of the software. I hope you can enjoy it. Although we have a lot of software packages to do the similar work in high precision GNSS positioning. You may have an alternative choice to use this software for comparison with some other software in processing to cross-validate whether you have achieved the good results. I hope it can be useful for your research. So here we have finished some basic processing using provided PPAR. For example, on static positioning using 24 hours of data. This is useful for some long-term monitoring of tectonics and glacier rebound analysis, and a reference frame maintenance as well. We also talked about the kinematic processing using 24 hours of data and 1 hour of data for short period of data. So these are very useful for seismic monitoring using for high rate data processing. You can use only 1 hour of data to have the seismic waveforms generated by ground shaking. And for 24 hours of kinematic processing can be good to for post-seismic, for early post-seismic data processing. You can see after the earthquake, especially during some after some large one, you will see there are very rapid post-seismic signals. I have students working on this for Chilean earthquake. So you can see after some large ones like 8.6 or 8.2, in the first 12 hours after the main shock, there are very fast movements of the coastal areas, coastal stations. So within whose magnitude can be up to a few centimeters. So this is quite significant for the analysis of the early post-seismic data processing. And also for 24 hours kinematic processing is also useful to volcanic eruption, pre-eruption analysis. So for the active volcanic activities, you can see that signal from the 24-hour data kinematic processing. Now we come to some advanced processing to solve some of your questions. For example, to how to use some other AC's products rather than Wuhan University's products. This is possible. And first, I want to review the basic structures of the software to retrieve the information that we may have forgot. For example, the configuration templates. So why do we prepare the configuration templates for you? This is because sometimes if you want to make the software to accommodate all kinds of processing scenarios, you have to change the options within the configuration file. And this is quite professional, and you needed to master a lot of GNSS high precision processing knowledge before you can do that. So we prepare these templates for you to facilitate your processing. For example, when you want to do some seismic data processing, you can use the template below here for high rate GNSS. Then you don't need to worry about whether you have set the options in the configuration file correctly. And also you want to process some airborne data, airborne GNSS data for photogrammetry or some other for airborne gravity. You can use the configuration template mobile. This will enable you to automatically process the data from a really moving platform. So this is why we prepare this, and this is the feedback from previous versions. Some users reported that they didn't know how to change the options correctly if they wanted to process this kind of data, So it's a lot of headache for them to understand what kind of options should be set. All right. So okay, sorry. Let's come to our first example. Okay, this is the because today for advanced features we needed to make some changes on the control file, and this cannot be done with only the control template files I prepared for you, because these advanced features is not usually needed by many users. They may have some special requests. For example, they need to use some other AC's products. Then we don't have this kind of automatic processing strategies available. So you have to change the control file yourself. You have to go into that file to make changes. So this will need some professional knowledge on how the processing is accomplished behind the software. This is so. Let me first show you some show you an example of show an example of the control file. So here, let's see. So this is the control file. We never opened it before in our last course. So here you see some options here. Although it's not so many options here. Actually, some options just repeated again and again. For example, the satellite list. It's very simple. You actually don't have many places to change anything here. You just need to know their meaning, and then you can do some work that you wanted to do. Let us start to introduce one by one, one block by one block. So this is the first block is the observation settings. These are basic settings for how you can deal with your observation. For example, the first field is the interval. Some people ask me about the interval here, and actually you don't need to worry about anything about the interval, because this field will be set by the script, the PPP3 automatically. It will read the sampling rate of the RANEX data from the command argument and then fill it here. So you don't need to worry about it. So interval specifies the data sampling rate. For example, it's 1 Hertz data or 50 Hertz data. So depending on your processing goal. And then the second one is the session time. The session time is the observation start time and the duration of the data processing. For example, I needed to process the data daily 24 hours of data. It starts from the 0 hour, 0 minutes, and 0 seconds of the day. This is for GPS time, and I need to process 24 hours of data. So it will be 86,400 seconds for one day. So this is session time, and this time will be set by the program, by the software itself as well. So you don't need to worry about it. You don't need to set it yourself, and it will process. So it will process all of the data within your file, and then the start time and the data duration will be the whole file. And then we come to the table directory specifies the path of the table, which contains the grid data for troposphere modeling, and it's central. This table directory is set automatically by the script as well, and it will point to the necessary tables that will be used by the software to correct for troposphere and the naming conventions. For example, you want to define the name of your file, of your resulting files, then you need to refer to a table of file names in the table directory. Then we come to the Runix directory. The Runix directory is usually set by the script as well. But if you want to process some data from other directories, rather than the default directories we set for you in the test processing, then you have to change this path automatically. Change this path yourself. For example, to the test data I sent to you today, sent you 2 days ago. So this is the Runix directory that you can change. Okay, this is the first part. The second part is the satellite products. Satellite product is quite direct, quite straightforward as well. So the first line is the product directory. The product directory will be set by the script as well. I suggest you don't change it, because if you put your you don't want to put your products here and there, that will mess your computer. So you can, all of the products will be downloaded automatically to that directory in the software, and you don't need to worry about anything about the product. And then we come to the satellite orbit clock, Earth rotation parameters. In short, it's ERP and quaternions of the satellite attitudes, and then code and phase bias. These are the 5 products needed by the software. The first 3, the orbit, clock, and the ERP, are required by the software to process any data. The last 2, quaternions and code bias and phase bias, can be optional. You don't always need them in your processing. For example, you just need some float solution, and then you don't need to do PPP AR, so you don't need the code or phase biases. Quaternions is not necessary as well, because the satellite attitudes can be modeled within the software using some other source code as well. So if you have some external satellite attitudes file, then it will read that attitudes instead of the modeling within the software itself. So here, if you want to, so here we need to pay attention to this part. Normally, if you don't want to use some other AC software products, then you can you don't need to worry about this field either. And the script will deal with the product downloading itself. It will download the product from Wuhan University to enable your precise point positioning processing. But if you want to use some other AC product, for example, from JPL, from Code, from ESA, from NGS, you need to change these 5 fields. For satellite orbit clock, you need to put their file name here to indicate that I needed to use some other AC products to process the data. All right, okay, let's come to the third part. The third block is data processing strategies, some details about the troposphere and the tides, and whether you are going to edit the data in a strict way or non-strict way. For example, the strict editing means the behavior of detecting outlier selection observations. We know some observations may have very bad quality. If you use some strict editing criteria, then you may remove a lot of data. And then the remaining data will be so few that you can't even estimate one epoch of positions. So we needed to change strict editing from yes to no to loosen some criteria for the data editing. This depends on the data quality. For example, if you use strict editing as yes, and a lot of observations are removed and you can't have results, you can try to use no option here for strict editing to have another running of the software to see whether you can have some reasonable results. And the second one is remove ambiguity. And this option should be placed in the following part for the ambiguity fixing module. It's this option specifies the behavior of ambiguity fixing. For example, you want to, if you have a long period of data of 24 hours of data, actually in this case, the ambiguity fixing will be quite easy, and you can use integer rounding to the nearest integers to resolve the ambiguities. But if you have short periods of data, for example, for just 1 hour or 30 minutes or 2 hours, then you need to use the variance covariance matrix to search for the correct integer candidates for your ambiguities. So this process will be complicated, and sometimes it will be risky. So I will show you some examples later on for the ambiguity fixing strategies. And then we come to the ZTD model and the HTG model. The ZTD model is for the zenith troposphere delay estimation strategies. We have 2 strategies. The first one is PWC, means the piecewise constant. And the second one, STO, means random walk estimation. Most people like the random walk estimation of the zenith troposphere delays. But sometimes if you process the 24 hours of data, the piecewise constant strategy for ZTD estimation would be better for you to achieve some higher precision for your vertical components of your coordinates. So this is some kind of strategy that you need to pay attention to. PWC should be followed by a period. For example, for 60 using commas, using semicolon, and 60 means 60 minutes. And we mean here we needed to estimate the zenith troposphere delay every 1 hour as a constant parameter, just like ambiguity as constant parameter over this 60 minutes. So it's just like piecewise constant estimation strategy. And then we come to the HTG model. This is for troposphere gradient estimation, for the horizontal gradient estimation. So we have 3 strategies. The first 2, PWC and STO, are similar to the strategies of the ZTD model. The last one, long, means we're not going to estimate gradients, because in some cases, for example, on some mobile platforms, to estimate the horizontal gradients doesn't make sense, because your platforms are moving always, and it may move for a long distance, for example, a few hundred kilometers. And then the estimation of horizontal gradients doesn't make sense, I think. So you can just turn it off here for the horizontal gradient. Horizontal gradient, troposphere gradient estimation is normally useful for 24-hour static data processing. It's not for kinematic ones or some moving platforms. And then we come to the second ionosphere correction, this I-node second. We're not going to talk about anything about second ionosphere correction here today. We can try that later on if you are interested in this. So if you turn this option on, the software will download the global ionosphere map from IGS to produce the second order ionosphere corrections for your data processing. And then the final one is tides. Tides means the solid earth tides, ocean tidal loading, and the pole tide. And these are 3 tide corrections recommended by IGS. A 4th one is the atmosphere pressure loading. The atmosphere pressure loading needs some correction tables from some specific institutions. It can be easily applied to the software, but we haven't done that because we see the atmosphere pressure loading. Sometimes the result is mixed. Sometimes you can get better results, but sometimes you may get worse results. So finally, we give up it. We use only 3 tidal model here. Why do we need to indicate these options here? Because normally when you process some ground station like 24-hour static data processing, you need to correct for solid earth tides, ocean tidal loading, and pole tide. But for some moving platforms like the airplanes is not connected with any ground stations. So it's over the sky, in the sky. So it doesn't make sense. In this case, you make corrections for solid earth tides because because the airplanes is not connected with the ground. And ocean tidal loading doesn't make sense either, and the pole tide doesn't make sense either here in this case. So for some mobile processing, like the airplanes and the ships, you must be careful to think about whether you should apply the tide corrections. You'd better turn them off here. For example, the solid earth tides, you should turn them off in the case of airplanes data processing. This kind of the solid earth tides can be up to a few tens of centimeters in the vertical component, so it has a great impact on the positioning. All right, then we come to the ambiguity fixing strategies. So here is a little bit confusing because we have a few numbers that is not so easily understandable. Here, the first one is ambiguity duration. This is the duration in seconds for resolvable ambiguity. Because of short periods of data, for example, for just for a few seconds, it's very hard for you to have a reasonable estimate for that kind of ambiguity, because you don't have a long period of data, and then the ambiguity estimates cannot converge in the least squares, and its precision is low. So in this case, it doesn't make sense. You can have a high probability to resolve correctly the ambiguities. So we must indicate the duration, the least duration for an eligible ambiguity to be resolved. So here the default value is 600 seconds, so just 10 minutes. So we have to use ambiguities longer than 10 minutes to be the possible candidate for ambiguity fixing. You can change this duration if you want. For example, 20 minutes or even 30 minutes. 30 minutes if you think your ambiguity fixing efficiency or correctness is impaired during data processing. Then the second one is the cutoff elevation. The cutoff elevation is similar for the quality control of eligible ambiguities. So sometimes your ambiguities for the satellites are in the low elevation. They are always located in the low elevations, and the measurements for this satellite are very noisy, and therefore your ambiguity estimates for this satellite will be very noisy as well, and its precision will be quite low. So in this case, you can set a cutoff elevation to exclude such ambiguities from the ambiguity fixing. And then that will lower the risks of incorrect fixing of ambiguities. The third one is the PCO on widening. This is a very special case. This is an unresolved problem in the IGS. So we are going to talk about it a few days later in the IGS telecom to talk about whether the antenna, PCO means the satellite antennas phase center offset. So we talked about this in our last course about on the antenna corrections within the PPP AR. So the PCO correction on the Melbourne Ubler is this option is useful when you wanted to use some other AC's product for ambiguity fixing, because their strategies for phase bias estimation may be different from ours. So then you need to turn this option on or off to be compatible with their products. If you are going to use Wuhan University products, then you don't need to pay any attention to this option. You just keep this option on, that is yes, to enable your PPP AR. But if you use some other ACs, you need to think about it. I will show you an example on this down. And then the fourth one is the wide lane, and the fifth one is narrow lane decision. And these two options are for the ambiguity fixing criteria during the integer cycle resolution. So we have three numbers for each. The first one is the deviation of your fractional part of the ambiguities from an integer. And the second one is the sigma of the ambiguities to be resolvable. Is the sigma must be smaller than this quantity. And 1,000 means the threshold for you to make a decision whether this ambiguity can be resolved or not. So this is just a basic. You don't need to change these values. If you want to change it, you must be very professional in high precision GNSS data processing. So I recommend you to just keep the values here and without any changes. The final one is the critical search, which is especially useful for lambda method to search for the correct integers for your candidate ambiguities. So here, we have 4 numbers. The first number is the highest number of ambiguities to be excluded. This one shows, all right, so I cannot, for example, I have 10 ambiguities to be resolved, but sometimes it's not easy to resolve all of the 10 ambiguities. So then you can use some partial ambiguity fixing. We can exclude 2 of them. We can only fix 8 of them, and that will make things easier. So you can successfully fix the ambiguities, and you got ambiguity fixed solution. This is so this exclusion of some ambiguities can be very useful if you fail to resolve all of the ambiguities. The second number is 4, which means the lowest number to be reserved in your candidate ambiguity subset. For example, you have 10, you can remove 2, 3, or 4 ambiguities from the 10 to enable ambiguity fixing. But the fewer number the ambiguities are, then the higher risk you are going to make an incorrect fixing. So you need to make sure to be very careful for this case. So you need to be alerted here if you wanted to change this quantity, these values here. Normally, you don't need to change them. You must have very professional knowledge of GNSS before you can do any decision on these quantities. Normally, 2 and 4 will be enough, because for some, in some cases, you have very bad data quality. For example, just 1 hour, and you see, oh, no matter what kind of effort I did, I cannot even resolve any of the ambiguity, and then you can try the partial ambiguity fixing here to enable the integer cycle resolution. Even if we have 10 ambiguities, but we can fix only 8 of them, the ambiguity fixed solution can be still good, even if we just exclude 2 of them, because ambiguity fixing the solve doesn't require that all of the ambiguities can be fixed. It can only fix some of them, and that will be enough. So this is the basic idea after this. Right, the last 2 numbers are some threshold for chi-square test and the ratio test. And these are for the validation of your ambiguity fixing. Okay, then we come to the satellite list. This is a long list in the control configuration file, and very simple. It just has 2 columns. The first column is the satellite PRN. We have GPS satellite, GLONASS satellite, Galileo satellite, and the 2 Beidou satellite, 2 and Beidou 3 constellations. And then we have the QZSS as well. So you think sometimes you have the default processing will accept all of the constellation if you have in your observation file. But sometimes you will want to see, oh, okay, I want to use only GPS satellites to do the processing, or I only wanted to use Beidou satellites to do the processing. Then you need to turn off some of the satellites. So here you can insert a sharp symbol in front of a GNSS PRN to exclude that satellite. I will show you this, how to do that. So you can just shut down some satellites from the processing. And then the second column of the column shows some numbers here, 1 or 3 or some other numbers you can think about. There's no limit of these numbers. The larger the number is, this number are the scaling factor of the weight of the satellite in your processing. We know, why do we set up this kind of values? Because you see, for some satellites, for some GEO satellites like C1, C2, C3, C4, and C5, they are the Beidou GEO satellites. This kind of satellites can also be used for PPP, but their orbits and clock quality are not comparable to other satellites, to other MEO satellites like GPS satellites, GLONASS satellites, and Galileo satellites. So their inclusion in your processing might degrade your processing quality. So you might want to exclude them using a sharp in front of them, but you can also set some larger weight scaling factor here. Sorry, weighting factor here to lower their contribution to your processing, to avoid some risk that they will degrade your processing quality. So I use a 3 here. That means their weight, their contribution will be downgraded to by 9 times. That is squared of 3 by 9 times. So in this case, you can avoid some risks brought by some bad satellites. This can frequently happen for some satellites that is in maneuver by the ground control center. They have signals, but their signal quality is bad. So you can downweight their observations in your processing. Okay, then we can come to the final block for station configuration. Usually you don't need to change anything here for station configuration, except for you wanted to try some other options for the GTD mapping function here. For example, we have 4 options for you. The default one is the global mapping function, GMF, and you can also try VMF1 and VMF3 for better modeling of the troposphere here. You have to change the modeling strategies here yourself. Otherwise, the default value is GMF, and if you don't have any solution to filling this part using the command arguments, you have to go into this configuration file to change it yourself. And then we come to the following. We have a lot of numbers here, right? So, okay, before that, we want to talk about the positioning mode, TP. This option here, we have 3 options: S for static solution, K for kinematic solution, and F for tightly constrained station coordinates to the IGS solutions. That means we wanted to use the IGS coordinates to re-estimate some other parameters of interest, such as the zenith troposphere delays. So we wanted to constrain tightly our coordinates to the IGS solutions. All right, then we make some detailed explanations on niche options here following the GMF. For example, the first one, the CLKM, means the receiver clock a priori constraint in the unit of the meter. You don't need to change it. This just is 9 kilometers constraint. And EV means the cutoff elevation angle for usable observation. So we have a cutoff elevation here again. This cutoff elevation is different from the previous one for ambiguities. This cutoff elevation here for EV for 7 degrees is for observation mask. So you don't need to use the observations from the satellites whose elevation is lower than 7 degrees. But the previous cutoff elevation for ambiguities, that's an elevation mask for eligible ambiguities to be sent to the ambiguity search program for the identification of integer candidates. So they are different. And then the third one is ZTD and the PODM. This shows the a priori constraint and process noise of zenith troposphere. So you can see the a priori constraint is about 20 centimeters, and the process noise is 0.004 meter per squared epoch. So that will depend on your sampling rate of your observations. So you need to carefully change this value if you wanted to use random walk strategy to estimate the troposphere for some professional applications. And then the fourth group is for horizontal gradient. Similarly, they have a priori constraint and process noise of troposphere gradients as well. So we use these two numbers here. We don't change them because the gradients can be easily estimated, and they don't have a lot of variation. So we use very small numbers here to constrain them. You don't need to change them unless you have very professional knowledge of GNSS to want to try some experiments to see how these values will affect your estimation of the gradients. Then we come to the storage noise and the carrier phase noise. So these are the two very important quantities to decide the weight of your observations in the processing. So the default value for range noise is 30 centimeters, and the default noise for carrier phase observation is 0.01 cycle. So their relative ratio of their weight is about 100 to 1. And then finally, we have three numbers here. These are a priori constraint for the coordinates for the X component, Y component, and Z component. So the default value are 10 meters. If you wanted to use the IGS solutions to constrain your coordinates, that uncertainty will be read from the IGS SINX file, and instead of these three numbers. So these three numbers will not be used in the F mode. In the F mode, the constraint, a priori constraint for the coordinates will be read from the IGS weekly solutions. All right, these are the simple introduction of the control file. So we are going to use here. I guess you must have a very brief impression on the meaning of these options, and then we are going to use these options to do some advanced processing. So at this moment, do you have any question on this? So I guess some people have got some questions. All right, take a look a moment, make sure the name should. All right, support high data processing in near real time, assuming that the data streaming is not an issue. In real time, no, this software cannot process real-time data. Real-time processing engine is another software in our department. This software is only for post-processing. If you have the products in time, then you can process the data as you want. But if you don't have the data, you don't have the satellite product, then you can't. We are enabling the storage of the real-time product streams like the satellite orbit stream and the satellite clock stream to be stored in real time on our FTP. And then you can download these real-time products as some kind of post-processing products to enable precise point positioning of your data. That's the philosophy of this software. HTG model is necessary for 24-hour static observations. Yes, I think so. I think if you wanted to have a good estimate of your horizontal gradient, troposphere gradient, you must have a longer period of observations. If you have only 1 hour of data, you wanted to estimate horizontal gradients, it'll be okay if you turn it on. The software can also estimate it using only 1 hour of data, but I don't think that makes sense because the precision of the gradient estimates will not be high enough. I always use longer data span to estimate the gradients. And how big are the effects of PCO phase center offset on satellite receiver distance? This depends because the PCO, the phase center offsets are different for different satellites, especially for Galileo satellites. For example, for the Galileo satellites, for the Z component, I mean the component towards the center of the Earth, that antenna center offset can be up to a few meters. So you can see, you can just imagine the satellite very huge. It has a few tons of a mass. So it's very huge satellite to fly in the space. So you can see the satellite antenna can be very long in the Z component, a few meters. So then you have to correct for the phase center offsets. if you want to use very precise satellite products, because the orbit products from the IGS are all referring to the center of mass rather than the center of the satellite antennas. So you have to make this correction in your data processing. Is their way to automatically exclude unhealthy without manual editing. Unhealthy, normally this processing, this identification for unhealthy satellites should be done by the IGS AC analysis centers before they release the satellite products. Some satellites is unhealthy. In the orbit determination program, you can see some large residuals from that satellites, and then you can exclude these satellites from your final product. So in your PPP processing, you will not see these satellites listed in your satellite table. So then you don't need to worry about anything about those unhealthy satellites. But this is not always the case, because in the past years we have tested a lot of products from different ACs. We have 8 ACs from the IGS, and some ACs may have these satellites for some days, but some other ACs may think that these satellites are not healthy, so they remove them. So there are some inconsistency between the satellite products, between the satellite lists in the products from different ACs. So then you can hardly say, all right, so this work can be done automatically by the AC or the software. The software will, the PPP software itself will use all of the satellites in the satellite table to do PPP, because it doesn't know which satellites are not healthy. There is no flag in the satellite product file that tells you, okay, this one's bad and you don't use it. If these satellites are really bad, that satellites will have been excluded by the ACs. And then you have to, I will show you some information, some clues in the processing that you can to help you identify the bad satellites. Should the elevation angle here be the same as the one in the previous computation file? Why this? Okay, 2 different locations. I have made this explanation before, because these 2 elevation settings are different. The first one is for ambiguities, and the second one is for usable observations. Normally, you should only change the second one. That means this one. You can change this one as you want. For example, you want to exclude observation from those below 15 degrees, and you can also set it to 0 to use all of the observations if you want. For the first cutoff elevation here, we set 15 degrees. This is because you'd better not change this. This is an empirical value from our past experiences. 15 degrees is good for a resolvable ambiguity. Lower elevation cutoff angles here will mean some noisy ambiguity estimates may be introduced into your ambiguity fixing processing, and this bad ambiguities may deteriorate your ambiguity fixing efficiency. So you don't need to worry about this. So just keep it here, and don't do any changes on these values. What you need to change is this value if you want. Then absolute. Okay. I think someone has answered this question, right? Okay. I think I have answered all of the questions. So let's come back to our first example here. Today we wanted to use the test data I sent you a few days ago. In the test data, we have one station from IGS, the AIRA station, with 24 hours of static data. And the second one is an airplane data. In China, it has about 3 hours of data, GPS only data from an airplane for photogrammetry. So you can see how we can process the airplane data using the software. So we first need to make an advanced directory to contain all of the computation results from today's experiments. And then in the first example and the third example, the runX directory, as I have said to you, this option here, I have changed it, right? You can see that you can copy the content template control file from the example directory to the advanced directory. And then you, whenever necessary, you need to change the Linux directory because you may place the data, the test data in some other data directory. So you need to pay attention to this. Otherwise, there are errors to be reported during your processing. Okay, let's close this. All right, so then we come to the first example. I want to make this larger for you. All right, okay, larger for you. All right. Here, I want to show you some the processing of GPS only solution versus multi-GNSS solutions. I know some of you guys may think the GPS only solution is good enough, so we can use only GPS. And this is the usual thought by many scientists, geoscience scientists. They think GPS is enough. But sometimes the multi-GNSS, you have more satellites, means you have more observations from the space. At least that will make your solutions more reliable compared to GPS only solutions. Sometimes you can have only, especially for climatic solution. For some epics, there are only 4 or 5 satellites to be observable at a single station. And then for climatic solution, for epic-wide solution, 4 or 5 satellites sometimes are not enough to produce a very precise position. And then multi-GNSS from other satellite constellations, from GLONASS, from Galileo, can contribute to the high precision of the epic-wise estimates. So here we use the AIRA station to do this work. So you need to copy the config template daily file. The template can be used and copied to the advanced directory. So let me show you here. So we have enough time today. I don't want to be in a hurry. For example, I have created advanced directory. You can use some other names if you want. I just use advanced because this corresponds to the advanced processing here. So I go into the advanced directory. I'll show you, I have processed all of the data yesterday for 2020 and 2021. And we have 3 template control file here. They are copied from the software example. In the software directory, example directory, we have the 4 control templates there. So you can copy them here for separate processing. So here we can open the daily control file. So you see here. All right, so I haven't changed this. So here, the first thing is to, because I put, for example, let me see. So let's go to the home directory and see the test data. So you can see the test data, we have a lot of things here. We have the ARA station to be placed in the test data directory. So I needed to change the Linux directory here to, let me see how I can do it. For example, I needed to change test data. Okay, I got it. So just save it, and then I can review some other options whether I need to change. Yes, strict add remove ambiguity. So I use random walk, right? You see here, I use random walk estimation strategy for ZTD, and I estimate gradients because I have 24 hours of data, and I don't apply any second order atmospheric delays. And I applied solid earth tides and ocean loading, tidal loading, because this station is connected to the ground, connected to the crust. So we needed to apply the tides corrections here. And ambiguities, we don't need to change anything here. Then we come to the satellite list. So in default, we use all of the satellites, right? So you see, we don't change anything here. If you wanted to use GPS only solution, then you can remove all of the other satellites. Just put what? Put a sharp here. So then the R01 is excluded from your processing. So you can see here. So we want to use only a GPS solution. So then all of the other satellites can be removed from your satellite list. You need to use some advanced VI operation technique to put sharp in front of all of the PRNs here. So I use, right, okay, I have done all of the, so I have excluded all of the satellites that are not GPS. You see here, so I don't change anything here. So I keep it the same here, I don't change anything. I only make 2 changes. The first one is where you can find your data, right, from a test data directory. And then the second one is to exclude the satellites that does not belong to GPS constellation. All right, there is a question here. Where is the test data folder? I think I have sent you the data a few days ago in the installation here. Just to sort it out. Double-get, that is version. All right. You can find the data here. Here, you can see here, this is the test data I sent you on September the 6th. So you need to download this test data to your directory. If you haven't done this, just try to to do this. All right. Okay, some other questions. Some stack, yes. All right, don't worry. All right, we will have a break, so you can sort out this problem during the break to download the data. Okay, so then we have excluded all of the non-GPS satellites. So then we save it. We save this control file, and we can use PPP3. Okay, I can first remove all of my previous computations, 2020 and 2021. I have removed it, all right? So just so we have nothing here. I want to recompute all of the solution PPP3, and we use contemplate daily. We use this control file, and this data is on the first day of 2020, right? 2020, first day. So we use 2020 0101 and the 2020 0101, the start date and the end date of your data processing, and then the AIRA, the station name here. And then we want to do kinematic processing epic-wise. And then the data sampling rate is 30 seconds. We want to use ambiguity fixing, make the yes, right? Okay, we want to, you got it? Because I have downloaded all of the products in our product directory, so the processing will not download the products again. It will continue to use the products I downloaded several days ago. So that processing will be easier, will be faster than previous days. So now we have the SPP executed successfully, and the SP3 warp to prepare the warpbits and tell it to pre-processing the data for some large outliers and cycle slips. Then we come into the iteration between LSQ, least squares, and radic. Radic means to identify some small cycle slips and outliers here. So we see here, this line shows actually the RMS of your residuals. So the larger the residuals are, the worse your satellites are. So now we have finished the processing. It's very fast because, okay, we have finished the processing. So let's go back to the screen output to see what happened just now. You see here. So in the previous data processing, we see there are several lines here. So now we have only one line reporting the residuals of your observations, right? Carrier phase residuals in the unit of millimeters. Because we have excluded all of the long GPS satellites, so there are only GPS satellites processed here, and we found some satellites bad, right? So in the first iteration, we found the G12 have an RMS of residuals of 53 millimeters. This is large compared to the other satellites like G01, G03. And after several iterations, for example, for the second iteration, we can see the residuals for G12 has been decreased from 53 to 7, right? 7 millimeters. So this is the contribution from the iteration to detect some smaller cycle slips and smaller outliers. So here you can see the RMS has become much better compared to the first iteration. You can see finally we have, so this is the final iteration. We have all of the RMS of the residuals smaller than 10 millimeters, except for G21, and all of the others are very good example, good observation, good residuals. This shows the high quality of the AIRA stations, so AIRA stations. And then we come to the ambiguity fixing part. So this is the summary for the ambiguity fixing status. So you see here for the GPS, this is G for GPS ambiguity fixing. Its fixing rate is about 76% for all ambiguities. So we have a large number of ambiguity here. But after we find the independent subset of the ambiguities, for example, the last line here, we can see the ambiguity fixing rates can be recalculated to be about 92 or 93% of ambiguities can be fixed. So that's actually 39 ambiguities out of 42 are fixed during the processing. So this is the performance for ambiguity fixing. And then the final solution will be will introduce the ambiguity constraint. So that is a conf file, CON file produced by the ambiguity fixing process. And that conf file will be introduced into the list squares to achieve the ambiguity fix solution here. So this is the, so let's see what happened here. We have a new directory 2020, and we go to 001 day, and we find that, okay, let's see, we find that we have the solution files here from different station, right? So you see the kinematic solution here from kin file, we are doing kinematic solution, and this shows the information we use for the processing, for example, in the kinematic mode, and the strict editing, yes, and the start date and end date and the epoch, and the sampling rate 30 seconds, 7 degrees for masked angle, and a priori noise for the pseudo range and for carrier phase, and what kind of products you use for the processing, and the set antenna antex file, the antenna PCO and PCD values, and the troposphere zenith troposphere estimation strategies for random walk STO, and then the gradient and second atmosphere no, and these are the ties to be applied to the processing. And this line shows the ambiguities to be fixed in your processing. So we have fixed ambiguities, yes, and we fixed 39 GPS ambiguities, Galileo 0, Beidou 0, and QZ 0, because we have excluded all of the non-GPS satellites. So these are the information. And now we have the field description here for the first column, second column, the third column shows the X, Y, Z coordinates and the latitude, the longitude, and height, the number of satellites, and the position, dilution of precision, the p-dot value. So this shows the X, Y, Z coordinates for each epoch for every 30 seconds here. So until here, right? Until the end of the day. So here, I want to show you something interesting here. I saw one star symbol here in the file. Let me go back to, go to the first line. Okay, see, you can see that at this epoch, for the second of the day, 3,150 seconds, we have a star here, right? We have a star here. This star here shows this solution is not so reliable because we have only 4 GPS satellites to contribute to this epoch. The 4, the 4 satellites are the least number to enable a processing, right? You have a 4th, you have 3 satellites to to calculate your X, Y, Z coordinates, and the 4th satellite to determine your receiver clock. So this is a common knowledge for GPS. So if you have only 4 satellites, that means we have no redundancy in the processing, and the resulting positions here may not correct, may not reliable. So this is the report from the kin file. So you see here, for most epoch, there are only 5 GPS satellites to contribute to epoch-wise processing. And this can be problematic because you are walking on the rope. And sometimes maybe just 2 or 3 satellites, and you will lose the possibility to resolve NFIC. So this just justifies why we need to use MultiGeneration. So we come to, so let's first save this file, because we are, when we are running the MultiGeneration solution, the file may be overridden. So then we have to, for example, we keep this file for comparison. We use GPS, all right, GPS. So let's plot king file. So when you use plot king file, you can check its usage here is followed by a king file, and the file name means the PNG file name. So what kind of file name you want to use for this processing? For example, here, let us plot it. So this is the GPS solution, right? So it looks good, even if we have only 5 satellites to do the kinematic processing for the horizontal position and the vertical position, and just 1 to 3 centimeters is really good. But the MultiGeneration can do better compared to this solution. So I'll show you here later on. Let's close it. We go back to right. So we go back to the outer directory, and we open the configuration file again, and we want to use all of the constellations. So we remove the sharp symbol here. All right, let me see. Okay. All right, so then we turn all of the satellites on. Right, you see here, right? You see here on, and then we run that command again. Let me see. All right, it's PPP3 here. So the same command to be executed here for ARA, the K mode, and 30 seconds. And yes, and then we press it again to have the MultiGeneration kinematic solution to be this will take some longer time because we have more satellites to be processed. So you see here, you will see some difference here, right? You see here, in the previous processing, we have only 2 lines here to show the GPS performance. Now we have 6 lines containing the Galileo satellites as well as the GLONASS satellites. The first iteration report very large RMS of residuals, and the second iteration, all of the residuals have been decreased to some reasonable level to around 10 millimeters compared to the first, right? So we have 3 constellations here. All right. Just a minute. All right. Do you have any questions? Oh, no questions here. Come back to. So you can see here now, all 3 constellations have similar data quality. You may think GPS has the highest data quality, but actually GLONASS and Galileo have similar data quality to GPS. They are comparable, so they can be combined together without degrading any other satellite constellations. So see here, let's come back to here. All right, so here, the final iteration. The final iteration you see here, the 6 lines here, the residuals from GPS are similar to Galileo. Galileo is really good. So you can see their residuals are smaller than 1 centimeter, just a few millimeters. GLONASS is a little bit worse compared to GPS and Galileo, but more or less the same, not so large distance between the 3 constellations. All right, let's come to the second part, which is ambiguity fixing status. So we see here, we have 1 more lines to show here. That is for Galileo, E for Galileo. The Galileo ambiguity fixing rate can be a little bit higher than GPS. So we have the 90% ambiguity fixed for for Galileo satellites, and in total, if we identify the independent ambiguities, just like IND means independent for all GNSS constellations, we can see the fixing rate can be up to 98%. So that means 63 ambiguities out of 64 are fixed in the processing. And this, the last line matters in our ambiguity fixing process. The first 3 lines are just some statistics for you to analyze the data quality. All right, now we introduce the constraint here, and we got the ambiguity fix solution. So we go into the directory to see what's happened there. So we see here the previous solution King file we have saved here because we have changed the name. If you don't change the name, then the previous results will be overridden by the following processing. So because they will use the same file names. So now we have 2 files. We open the King file. After the multi-GNSS processing, we come to the data body here. So for each line, let's open another one as well. So here, so in here, we open 2 files simultaneously for GPS only solutions here, and we make a comparison for for this epoch. For 3150, right? Let's find 3150 as well for the multi-GNSS solution. 3150, okay, 3150 here. Now we don't have any star symbols here anymore because we have 15 satellites at this epoch to contribute to the data processing. So we have 4 GPS satellites, just as in the previous case, 4 GPS satellites. But we also have 5 GLONASS satellites and 6 Galileo satellites. So we have much more satellites compared to the GPS one. All right. So then let's compare their precisions. We wanted to compare our coordinates with the IGS solutions because that makes things more objective. So how can we find the IGS solution for this station? So ARRA. So I told you the command to look for the IGS solution, weekly solutions, the truth benchmark. So 2020 and 0101. So let's see how IGS compute the result of the IGS solutions. So this is the IGS solution coordinates, right? The correct one or the truth benchmark. So we compare our coordinates with this. We plot King file. So we need to compare 2 file to let's say AIRA GPS and the coordinates from the truth benchmark here, and we got the first solution here, right? So this is the solution for GPS, and then we come to the second solution for multi-GNSS, right? So ARA multi and compared with the same coordinates, right? Compared with the same coordinates, and we got the second one here. Right, so this is the second solution for multi-GNSS. Let's open the 2 files simultaneously. Open AIRA GPS PNG and AIRA multi. So open them simultaneously. All right, this is how it shows in. All right, this is for GPS only solutions for the 3 components. We can see the R lengths here for 1 centimeter, and 1 and 2 centimeters for north, and 3 centimeters for vertical. And for the multi-GNSS, we can see the horizontal component can be improved by a little bit to better than 1 centimeter. And the vertical is 1.08, and the GPS is 1.668. And the vertical for GPS is 3.1, and for multi-GNSS is 2.82. So you may think there is a little bit of improvement, but this improvement should be accounted for in the whole processing because we are processing 24 hours of data. There's an average impact on the calculation of the statistics. So you can see this improvement can still be very significant compared to GPS only solution. And because the 2 figures are not plotted simultaneously, we see the vertical scale here are not different. For GPS, it's from -10 to 10 centimeters, but for multi-generation solutions, from -5 to 5 centimeters. That means the largest. There are some outlier solutions here, which is not feasible because it is quite small. That is out of the 10 centimeters, some outlier solutions. That's why the plot has a value, has a vertical range from -10 to 10 centimeters. But for multi-generation solutions, we don't have such outlier solutions. So all of the solutions are within with -5 to 5 centimeters here. So that means the positioning are more reliable compared to GPS only solution. In the case of we have more GPS more satellites to be available. So let's see the last line of figures. We show the number of satellites and the p-dot value. And this shows the number of satellites. You can see the satellites sometimes is even close to 5 for GPS only constellation. The GPS can be up to 10 as well. So sometimes you have more GPS satellites to be used by positioning here. But some frequently we can only have 5 or 7 satellites to be used for epic-wise positioning here. But for multi-GNSS, you can see we always have more than 10 satellites to be available for processing, except in this case, some problem here because of the loss of the signals from multiple constellations. But normally we have much more satellites to be available for the processing. Right. So okay, I think we can have a break now, and I can answer some of your questions, and we can resume this class in about 10 minutes. Do you have any question on this? Let me see. The multipath error. Multipath error is you should have some independent program to deal with multipath error because you need to. I'll tell you, you want to start in the multipath error. You must, for example, you must open the residual file. You see here, RES file, residual file. You needed to extract the multipath error from the residual file. So here we have the GPS satellites and the GLONASS satellites and the Galileo satellites. So this column, so you see here, this column shows the carrier phase residuals. Normally, the multipath effects cannot be addressed using any high precision software directly. And you have to extract the multipath signatures from the residual file from the previous day, and then make them as a correction product to be applied to the following day for multipath mitigation. So here we have, this is in the term in the unit of meters. So you can see the multipath effect for the GPS for the satellite are quite small, but I can show you how the multipath looks like, what the multipath looks like. You can use plot res pi. Oh, sorry, plot res pi. Okay, you can see how to use it, and the res file. Okay, which satellite? We can set G10. Let's say G10. All right. See whether we have G10. Okay, we have G10. It's not so long. All right. Let's see whether we can. This is a residual, so you can see the multipath signatures from the G10 from time series of the residuals. For example, you can. All right. Okay, got it. So this is the zoomed in. We have zoomed in this plot, so you can see the multipath signatures here, right? So this is elevation angle. So the lower elevations means more severe multipath effects. So you can see here there are some fluctuation of your residuals for the carrier phase, and this is typically caused by multipath effects. So you needed to extract these signatures from your observation residuals and apply these residuals to your processing of your following data. So then you can correct for them for improved processing. So this is the multipath signatures like this. Normally, if you have high elevation satellites, so here, and then the multipath can be smaller, so you can see very flat. very flat residuals close to 0. And if you have multipath effects, it may have some fluctuation like this, just some downward or upward fluctuation of your residuals, and that can be extracted. And this kind of signature can be extracted from your processing to do the multipath mitigation. But unfortunately, our PPAR software is not dedicated to this application. Its main function is to process the raw data and produce the solution for you. And if you want to apply the multipath mitigation, you have to make some independent software to analyze the residual file. The residual file are already here. So what you need to do is read this residual file for the second column for each satellite at each epoch, and then to low pass filter the residuals to get templates, to get multipath correction templates. And then this template can be applied to the following day from your raw observations to be removed from your raw observations. And then you can have improved the climatic epoch, climatic position estimates, right? Check model will be available for the test. I will send you the slides later on. So after this class. Let me show you some more. Let me see whether we can have some more typical multipath effect. Let's see E05. See E05. Let me see whether longer time series, no cellular residual for E05, E10 or E05. E05. This is too short as well. Too short as well. Short as well. G13. G13. This is too short as well. So we have two parts of the G30. Let's say G30. This is too short. Too short as well. G30. Okay, we have longer time series for this satellite. So you see, let me show you some more multipath signatures here. So you can have a look at this. All right, okay. You see here, so normally you have a high elevation satellite observations. The residuals can be close to 0, right? So you can see this part is quite close to 0. But after, for low elevation observations here, you see there's some minor fluctuation, right? Some minor curvature of your residual time series. So these are the multipath effects caused. So the multipath effects can be very rich of frequency content. It can be very short periods of data, periods of signals. It can also be longer periods of signals, up to a few hours. So it depends on your surroundings of the stations. Receive antenna information model. And I have no metadata. Yes, the receiver antenna information are obtained from the observation itself. We don't prepare any additional metadata table to prepare the observation antenna or whatever information here. Actually, the major information for the metadata of receivers is these two lines. So the antenna type, so what kind of antennas does it use, and what kind of receiver does it use, and the firmware version. And that sometimes this can be important for ambiguity fixing, and this is important for coordinate correction. These are the two major type of information that is required by the software. Some other software will require the users to prepare a metadata table to hold this information for the stations, but we don't do it here because we wanted the users to feel more confident than to prepare such kind of tables, because such kind of tables will need to be carefully checked by the users themselves. It cannot be automatically produced if you don't have such kind of information. and that will be some kind of headache for users, for some users of preliminary knowledge of GNSS. So, but if you don't have any information, if your antenna information is vacant here, there is a warning in your processing, and that warning will tell you if you don't have this kind of antenna information, the antenna offset and antenna variation will be set 0 in your processing. That means your coordinates actually refer to your antenna phase center rather than your marker points of that station. So this is why we want to make the software easier to be used. So we just don't ask the author, ask the users to prepare such metadata table. It's amazing the commands that I was supposed to modify because it's not finding the BRDC file that is downloaded. The BRDC file should be downloaded automatically by the software. We have the, so you see here, let me show you again I'm showing you again here. All right. So this is the BRDC file, the BRDM file downloaded by the software. I can remove it. I can remove it to process again, and the software actually can do it for you. You don't need to worry about that if you have internet access. So I can remove it, and then we don't have any BRDC file for AIRA here, and we come back to here to process the data again to see where it downloaded the, all right, where it downloaded the broadcast. Okay, we got here. So we have the PDP3 here, and let's go again. All right. Okay, I just stop it. You see here, it's downloading the BRDC file here. So BRDC file is downloaded successfully, and change the name to BRDM. And then we come back to the test data. So the BRDC file appear again here, right? So the BRDM001, I have removed it. So just now I have removed this file for your reference, right? So you see the file is downloaded again. If you can't find it, you should check whether you have internet access from your computer and whether, right. Test data, right? That means you didn't make correctly the creation of your advanced directory. You have to. Okay, I can put my control file in the. Let me see, advanced. All right, sorry. I'll put my control file here. Right. Okay, I sent it to you. You can use control file. You need to create the. You need to create a directory called test data or any other name you feel good. All right, so you need to create a test data and then create a, I did my processing in an advanced directory here. So you can use any other names if you want, but you need to indicate the correct name, here, Linux directory, user JGeng test data. If you are in a Linux system, you use home here, and then your user account, and then the directory test data. This is an example. You can use any other name if you want to, but you have to make them correctly. Otherwise, the script cannot find your data, cannot find where your data are. So let's make sure. Share. Let me see. Broadcast can help. Oh, Sarah. For Sarah, this problem is your wget doesn't work. Wget doesn't work. I thought you have resolved the problem, but can you just turn off the show progress, option in your in your script, the PDP3? You can. I saw some people a few days ago showing that he or she just turn off the show progress option from the wget, and then it works. It may be because we are using some higher version of wget. It has the show progress option, so we use it. If you use some lower version, then it doesn't have that option, and that may fail. Can you try to just turn it off and then to try it again? Wget problem. So I sometimes don't understand why wget doesn't work. All right, doesn't work. When you download a text file, I tried different test data, but it could not find IDS-OT. I think it should be able to download 2163. This file, if it doesn't have, if it can't download this antex file, that means the IGS doesn't provide it, right? I think we have. I downloaded this file before. Let me see. Which it will download the antex file according to your data. So it should be no problem. We are not fixed to one antex file. Let me go to my my table here. So we see, oh, I downloaded the 2 antex file here automatically using the software. So we are using 2148. This is the latest one I used. I don't know why you are using. Do we really have the 2163? Let me see. G week 2163.4. Yes, it's the year. It's this year. Let me see whether we have that file. Let me see, IGS. IGS general. It has the antenna. IGS GLONASS. GPS, right? Or no? General mail product. Station should be station, right? General. Okay, we can find the antex file here, PCV archive, right? PCV archive. So I think the latest one is 2148. I don't know why you are looking for 2163.
Hi.
It's
yeah, I tried some data from a few days ago, and I believe it's getting the name from the orbit file. It's the Wuhan orbit file.
Okay. Right. Yeah, I think so. But from my understanding, this is the latest one released by IGS. Maybe IGS hasn't uploaded the 2163 antex file to their folder. So I will check that with my students to see what's the problem with this. Okay.
It should do it automatically though.
Yeah, automatically to use the antex file that corresponds to your Warbit and Quark products. This correspondence will be made by the software itself. You don't need to worry about that. If you can't find it, that's because in this directory we cannot find the latest one. So from here you can see the latest one is actually 2148. There should be something wrong with the IGS website. So oh, here you can see here.
Okay, I understand. Okay.
You see here. Yeah, you see here. It's not in the PCP archive. All right, I will tell my students this is maybe problematic. So we should the Warbit generation process is different from the software. So it's looking for some antex file that is located in some different places. but the PPAR software is looking for the antenna file from here, so it needs from here, so it cannot find it. All right,
Hey,
this is a
thank you.
good question. I will fix it. I'll fix it. All right. Problem was that I can use test data in my control app to have the whole path name used. Got it now. Yes, you can. You need to use user. You need to use the absolute path. You cannot use a tilde here. Because I never tried here, but it should be able to recognize the tilde here. But maybe because some problem for the software, for the program to recognize the tilde to represent your home directory. I don't know, but you'd better use the absolute path to reduce the problems. Okay, for the question, I think just now we are talking about the antex file for 2163. I think the program just reporting that it can find this file, and it will download the file here, download this file. For example, it will download this IGS1 IGS14 ATX file instead. So if you can find this 2163, and actually in the outer directory from IGS, this file is just a link to this file. So actually, although it was reporting an error for this, but I believe your process is still went on, and without any problem, it will download this file instead. But this file is just is a link. You can see they have the same size for it's exaggerated. You can see this file, so that's 18 megabytes, and this file is approximately 18 megabytes as well. So these two files are the same. This 2163 are the latest. So I think should be no problem to do that. I saw that problem before, and it will download this file instead. And this file is actually referred to this one, so it should be okay. Okay, so I think we have only one hour left. We need to speed up the processing here. So we still have 3 examples to show here. These are the, okay, we have finished the discussion on, let me see, all right, discussion on the multi-GNSS versus GPS-only processing. And then we come to, all right, we have finished all of this. Let's go to the second example. So some of you guys may be interested in using other IGS products. We have prepared these products for you in the test data directory. You see here. Let me see here. All right, you got this. If you download my test data directory successfully, you can see COM. You can see some files started with COM. And these are the products from code. Actually, each IGS AC, including JPL and ESA and GS, all have their own satellite products started with different names, but you need to know where to download them. Normally from the CDDIS in NASA, you can find all of the products from different ACs or from some other FTP areas or HTTP areas. This software, unfortunately, cannot download those products automatically for you because that will complicate the scripts, and it will cause a lot of problems. So, but you can download the products yourself and put them in the right place, and the software will recognize these products and process the data using these products instead of the Wuhan University products. So here, I will show you how to do that. Here is quite straightforward. You actually don't need to change a lot of things here. You can still use the configure we use the configure template hourly control file to process 1 hour of data using the COM product, using the product from code. So you can download their products from these FTP areas. You can see a lot of products, all kinds of varieties of products there to be used by any PPP users. There's one note here. For the Wuhan University products, you don't need to, because their products are downloaded by the script automatically, and normally the products are compressed files, and you don't need to uncompress them yourself. But for the products from other ACs, you have to decompress them before they can be recognized. So once you have got the files from the code FTP here, they are compressed files. You cannot just use put the compressed files in the product directory and then run PDP3 to get the results. In that case, the PDP3 cannot recognize these files, and there will be an error report. So you have to uncompress them. Why do we not uncompress these files for you? This is because different ACs use different decompression software. Sometimes they use unzip, sometimes they use gunzip. Some other AC may use some very strange unzip tools. So it's quite a headache for us to be adapted to different kinds of compression and uncompression tools. So then we finally abandoned this, and we ask the users to uncompress the files themselves if they wanted to use some other AC's product. Okay, then we have finished this. Now we come to how we can change the control file for you. Now I have copied the hourly template from the example directory here to the advanced directory, right? You see here, the advanced. Let's open it, where we need to change. So the first one is this path need not to be changed because we are going to use CCJ2 station. That station is already in the data directory of the software. So you can go to so you see here, this is the software directory, Pride PPR version 2.1. You go to example and then data. So you got 2 directory for 2021, 21, and on the day 210, you can see the CCJ2 station there. So then we don't need to change anything here. We just keep it. So using this path to find the Redux file. Okay, we got it. Now we come to the most important part for the default. But here, because we wanted to use COM product, so we cannot use default. The default means we are going to use the Wuhan University product. If you want to use COM products, we have to change this one by one. You manually, for example, you copy this. Copy this. All right, copy this orbit file here. Let me see. Copy them one by one. Let me see, one by one. Right, you have to change the name for clock. It's ended with CLK. For ERP, then the ERP. For quaternions, it's standard with OBX. And then for code and bytes for BIA. So these are the 5 files provided by code. You can use them for the processing. All right. Then we have done here. So then we are going to use their product for the processing. And then strict editing, yes. So remove ambiguity, no. We should use, we are going to use the ambiguity search based on the lambda method. So we use no here and PwC 60. We have only 1 hour of data. So we estimate only 1 ZTD parameters for this station. Then we don't need to change anything here, right? So we just use all of the satellites and then it's done. And then we save it. So now using PDP3 and config template hourly, and we have the 2021 is on the day of the year 210. That's July the 29th. So 2021, July the 29th. And CCJ2 station for K mode and 30 seconds sampling rate and ambiguity resolution enabled. So then we come to here. We got the processing. So now you see here, it's using the COM product for Warbit, right? For Warbit transformation here. This is COM product. And now we are, all right. So this is the iteration for ambiguity fixing, right? And fixing, no, it doesn't resolve any ambiguities here, right? Okay, and we have the solution here, right? Let's see the processing, the iteration for the processing. So using COM product, you can see the QZS satellites, J01 and 02 and 03 are also processed. It has 4 constellations. For the Wuhan University product, we don't have any QZS satellite orbits product available. You can use COM product to process QZS satellite observations. And then with Galileo satellites, and we have the GLONASS satellites, and we have the GPS as well. So after the processing, we can see the final iteration. The observation quality are very comparable with respect to each GNSS. The QZS seems better than the previous 3, but they have fewer satellites compared to Galileo and the GPS. These are the 4 constellations, and this is ambiguity fixing, right? And here we have the ambiguity constraint found, and we do the ambiguity fix solutions. So we come to but now we see here, we do not fix any ambiguities. Right here, we have a problem here. So no more can be fixed. So here 0 out of 14 fixed. The fixing rate is 0%. So you may be confused about this. So why can't we fix the ambiguities using COM products? And from the Galileo line here, we can see the wide lane fixing rate is quite low. It's only 52%. And this is because we forgot to modify one option in our data processing. So we come back to hourly. So we only changed this part for COM product. But as I have told you, the PCO wide lane part, the PCO here we have to change it to from yes to no before we can, for example, here. First example here, this is no. Because COM products looks different from ours, and they don't do this correction on their product. We're going to talk about this in a few days with an IGS Telecom to have an agreement on this correction. But anyway, this is not the business here. We just change it to no, and we run it again to see whether the ambiguity fixing can be better. So we run it again, and we come to this part again to see the results. Right, let me see. Right, no question here. All right, now you see the ambiguity fixing much better, right? So now 12 out of 14 can be fixed. The fixing rate is about 85%, and the Galileo ambiguity fixing rate for wide lane is 100% compared to 50% before. So this is one of the attentions you need to pay for using COMS product to do ambiguity fixing here. So this is the result. So let's see our result in 2021 on the day 210, and we have CCJ2 station here, right? So this is the kinematic results. So let's plot king file CCJ2, and right. So this is the processing result. This is the result for the processing. So here. Okay, sorry. Okay, sorry. This is from this is the result by using COM product. You may be interested in what's the result if we are using Wuhan University's product. So we can make a comparison. We can make a comparison here on their difference. Normally there shouldn't be any large difference, but the results are different. So see here we go back to hourly, and we change it to default. Let me see. Okay, and then we needed to change this back to yes. So to yes. Let's do it again to see. All right, to see. You can see now it's using Wuhan University product, see, SP3 warp to transform the WUM product for the orbit. So here now, and we don't have QZS satellite product, so the QZS satellites are excluded from our processing. We use only GPS, GLONASS, and Galileo satellites. So here, so now the fixing rate is the same as the COM product, right? So from 12 out of 14, and the fixing rate for wide lane is a little bit lower compared to COM products here. Let's go to the 2021 and 210 for the results. So we have already, the previous result has been overridden by the new results. So we have reserved only one picture here from the COM product. Now we plot a second picture for the CCJ2 WM. So you see here, so we see here, let's make a comparison. CCJ2 PNG, CCJ2 WM. So we have two results here, and the first one is from COM product, and the second one is from the Wuhan University product. So normally they are very similar, no large difference here compared in terms of the time series within 1 hour. So we see no large difference here, quite the same. All right, okay, this is the second experiment for using some other AC product here. So do you have no question? Right, good. Okay, this is the second example, and we just leave it here because we have two more examples to be shown. Then we come to the mobile platforms. All right, some questions here. Drop the modifier method in the second case. All right, great. Let's. Oh, I have changed it back to. I have changed it back to the Wuhan products. So you need to. So you need to actually you can find this a template file from our software directory. So this example is very straightforward. We are processing a mobile platform data. This is an airplane data in China, over China on the oceans. So you see here it flies for a longer distance, very long, a few hundred kilometers off the coast. It's collected on November the 21st, 2020. And its sampling rate is 0.1 seconds, so it's 10 Hz data. But unfortunately, it has only GPS data, so we cannot do any multi-GNSS processing. For the 10 Hz data, the processing for 3 hours will be quite long, and you may wait for 5 minutes before the computation can be finished. So let's come to the processing details. So you need to can copy the template mobile from your software package to the advanced directory, the example directory today we are using, and then to change the right next directory to the test data directory, because I have uploaded the rover, the airplane data to that directory. And note, if you are doing this processing, you have to turn off the tide correction, because the airplane is not connected to the ground, and the correction for solid earth tides doesn't make sense. So you don't need to change that. So let's come to the first directory of advanced. I have copied this mobile control file here. Let's open it. So what kind of correction we should make? So here for the right next directory, I have changed it to the test data directory, right? You see here, and I use default satellite product from Wuhan University, and then for strict editing, you see strict editing, I use no, because for airplane data, for mobile platforms, the data quality sometimes not so good, because the airplane is shaking during their flight, and that kind of shaking can cause a lot of problems for GPS receivers to properly decorrelate their carrier phase signals from the pseudo-range signals. So here, I normally use set strict editing as no to increase the data volume for the processing. And the remove ambiguity, yes, because I'm not going to use the number method to search for the ambiguities. And the ZTD model, STL random walk, and HGG model for the horizontal troposphere gradient, we don't estimate it because this is an airplane. It's flying about 100 kilometers, several hundred kilometers, and it doesn't make sense to estimate this kind of parameter in your processing. You can estimate it, but it doesn't make sense. And for the second answer, don't do it. For the tide, you see, for tide, normally we have. Let me show you a comparison for the past setting. So for the daily file, you see, you can make a comparison between these two files. This is for the daily control file. We use solid, ocean, and the pole for 3 tides correction. But for the flight data, we use none because we don't need to correct for this. It's an airplane. It's not a ground station. So here, and ambiguity, you don't need to change anything here, and anything change here, you just keep it the same. So this is all we needed to do for the control file. I'll upload this control file to you later on. Okay, let's see the question. Do you want to use straight and no also for kinematic ground stations caused by large? No. For ground station of large earthquake, because for that kind of station, they are actually static most of the time. So that kind of data quality quite good. It's static stations, and to be free from any obstruction of signals by the trees or buildings around. So then you can use a strict yes for the data editing of this kind of data. For airplanes, because for the mobile platforms, for some kind of buoy on the ocean and the ships on the ocean, because of the shaking of the platform, because of the shaking of the platform, the data quality sometimes cannot be so good. But you can try both. You can try yes to do the processing and try no again to do the processing again to compare the results to see which one is better, and then you can use which one. So it's just a general rule or general guidance for you to process data, but it's not so compulsory. So you can try both to see. But for ground stations like the IGS stations or the UNEFCO NOTAA stations, you can always use yes for a better data quality check of your observations. So this is the explanation on this. And let's close this and let's close this. Okay, before we process data, let's go to the test directory to see what the data look like. So you can see here, there is a ROF9 station name. This is the airplane data. It has a very large volume. It's about 200 megabytes. 200 megabytes on day 326 for the year 2020. Let's open it. I hope you have found it, right? You have found it. So here, this is in the format of RANX2, right? For RANX2, and we have only GPS data. So we have only, you can see here from the data body, we have only GPS data here. And here we have the problem just mentioned by some participants about the antenna type. So it has unknown here. This usually happens for some privately collected data. For some private users, it has its own data. Sometimes he doesn't know how to set the antenna information for that RANX file, so it will just vacant it. Then this vacant information will be set unknown by the RANX by the receiver, and you don't have it. I will suggest you modify this head part manually before you do the processing. Otherwise, the antenna offset will be set 0, and your processing results will refer to your receiver antenna phase center rather than your reference point for the antenna. So here, just pay attention to. And this file is not so standard, you see, it's not so standard. So you can just manually make corrections on the head part of this file. All right, so you can see this file is 10 Hz data. So this is 21.3, and for the first epoch, and for second epoch, 21.4. So it's 10 is sampling rate is 0.1 seconds, and is so with 10 Hz data, 10 Hz. All right, so because it's a long range flying, so we let's see what happened here. PDP3, and we use mobile. And it's okay, 2020. Okay, let's see what date is it. What day? It's all right. It's okay, November the 21st, 11:21. So it's 11:21, 2020, 11:21, and we have ROF9 station kinematic, and it's 10 Hz, so 0.1 seconds, and we resolve ambiguities. Yes, so this is command we need to input, right? All right, so that will take a long time because this is prepare initial position for ROF9. It's 3 hours, so 10 Hz data is a very huge file, and you need to wait for some time before it can be processed. So before that, let's go to the slides to see. Let's wait here. To see. It just take about 5 minutes to finish the data processing. The data quality for this airplane is quite good. So the iteration for data editing doesn't take a long time before we can see the final results. Here, we must pay attention to this. Sometimes this is airborne data. Sometimes you may process the shipborne data on the ocean. So then you may be interested in whether you should apply the solid earth ties. The solid earth ties for the ships, they are they are of course on the ocean, and the ocean is connected with the solid Earth. So then the solid Earth tides can be applied to ships, but ocean tidal loading because of the ocean pressure on ocean mass pressure on the coastal areas, causing the coastal station to be downward movement. And this kind of ocean tidal loading cannot be applied in the case of shipborne data. So so sometimes for the platforms on the oceans and in the sky, you must be careful when you apply some kind of tidal corrections. Normally, these tidal corrections are only applied to static stations on the ground. For example, for the UNAVCO stations, for the IGES stations, these globally distributed stations are tightly connected with the crust. So you have to apply the tidal corrections to have a precise estimate consistent with the IGES weekly solutions. So you have to pay attention to this. And then this is the result. Okay, this is the, and then for the ambiguity resolution for airplane data does not always succeed because it's also because of the shaking of the airplane. The shaking of the airplane will cause the antenna to be tilted, right? And this tilting sometimes cannot be recorded by the airplane. If you have an inertial navigation system, you can record the attitude changes of your antenna, and you can apply this correction to augment the GNSS data processing. But this can be very complicated. If you don't have this inertial navigation system, then the shaking of the antennas because of the shaking of the airplane cannot be recorded. So in this case, that kind of shaking of antenna will cause some minor biases on your data processing, and these biases cannot be recognized or processed by the software, and actually cannot be processed by any software because it's unknown. And that kind of biases is non-integer biases, so it will be assimilated into the ambiguities to destroying their integer properties. So sometimes if you can't resolve the ambiguities for the airplane data, you can just set it to no to provide it. If you have a longer period of data, the ambiguity float solution can be already good enough for you for your following for your analysis. All right, so let's see what's the question. Would it be appropriate to apply the polar tidal correction to ship GPS data? Yes, I think so. For polar tidal corrections to shipborne the GPS data is fine. The polar tidal correction is quite small compared to solid Earth tides and the ocean tidal loading. It has minor impact on that, but you can for polar tidal corrections you can use for the shipborne data. That will make sense to do that. But that impact is quite small compared to the errors caused by the shaking of the ships. So the shaking of the ships can cause much larger errors than the polar tidal corrections. So it's sometimes even if you make that correction, it doesn't change a lot of things. All right. All right. Okay. We have begun to do the iteration for the data processing. So you can see the first iteration. We can see a lot of satellites have a huge residuals of carrier phase. This is because this is much worse compared to ground stations. You see, for the ground station, even for the first iteration of the least squares and the radic and residual editing, we don't see so large residuals for the observations. So we need iterations to do that processing to identify some minor cycle slips and outlier solutions caused by the shaking of the airplanes. And actually, this is a very small airplane. There is only one people on the airplane, and it's not a drone. It's not a drone. If it's a drone, it'll be more complicated to have a precise estimates for the airplane position. So this airplane is shaking very very hugely in the collection of the data. So you can see the results. The data quality is not as good as that of the ground stations, but you will see So you'll be patient for this kind of processing. For 10 Hertz data, it takes a long time. If you're processing 50 Hertz data, that is a sampling rate is 0.02 seconds. That will take a huge, rather long time than even this. For 3 hours, the 10 Hertz data is a really huge time to be waited. But just for about a few iterations, we can see the results can be produced from this processing. We see here. Okay, we got it. So you can see for the second iteration, because of the data editing here, we see the residuals can be decreased to a large extent from 303 millimeters to 8 millimeters. So overall, after the data editing, the GPS data quality for this airplane is quite good, right? It's quite good. It's not as worse as those of some ground stations. You can, I think only after this iteration, we can have the results to be available for everyone to use it. All right. Okay, we have a few, we have only 20 minutes left. So we have only one last example. This is the track. Let me show you later on. I want to show you the last example is troposphere estimation. Some of you guys may be interested in the troposphere rather than the positions. This troposphere estimation is quite straightforward as well. You only need to tightly constrain your coordinates to the IGS solutions, and then you use the random walk strategy to estimate the zenith troposphere, and you can have the epoch-wise troposphere estimates for that station. This is let me see. This is well, really long time to do that. Okay. Okay. Do you have any questions here? We can talk about it because we are waiting here. Actually, I should split this data into 3 parts, 1 hour for each part, and then that can decrease the processing time.
Can I ask a question while we wait, if you don't mind?
Yes, you can.
Yeah, sorry, I wasn't sure. So for the EGS products, can we only use the combined ones, or is it possible to like use GPS orbit and clock, Beidou orbits and clocks, so Galileo separately, but at the same time?
You want to mix?
Well, because like I think if I'm correct, they are currently providing individual GPS, individual Galileo, and individual GLONASS, and then there's a combined product. So I wonder if you can mix and match, and if you can, how to do that in the config file.
Oh, you mean you want to mix the products from different ACs, right? For example, you want to use the orbits from code, and then use the clocks from Wuhan University. You want to use this?
Oh well, no, I wouldn't do that. No, more in like I'm mostly talking about products for constellations that are provided separately.
Oh, you mean some product the
different constellations? Yeah.
The products are provided for each constellation individually. It's not combined product, right? So
yeah.
I think if you because we only accept one product file for 1 day, you can combine different days of product together. For example, here I'll show you. Let's make some longer explanation here for you to. And actually, here we can have as many products as we can. So this 5 line can accept multiple.
Okay, cool.
Multiple,
that sounds
multiple days of
cool.
Can accept multiple days of a product, but you need to make sure they are for the consecutive days. For each day of a product, you can use only 1 file. But in your case, you mean for different constellation will be in different files. And then actually what you want to put here is that, all right, for the first day, I have GPS products here. And for the first day, we have another file containing the GLONASS products where I have to put them here as well. This is really hard for the software to recognize this kind of condition. I think you'd better combine the products in advance together in one file. I mean, for the products for the same day have to be put in the same file. Otherwise, it's really weird to process this kind of scenarios. I mean,
thank you.
Actually, actually for IGS, all of the stations are all of the satellite products are put in one file for one day. So they never separate the products from different constellation into the individual file. It doesn't make sense. That will increase your storage and increase the complexity for the users to recognize the product, right? Okay, all right. Oh, sorry. We have got the information finished. So now we can see the ambiguity fixing rate here. It's antenna. You can see here there is a warning here. Antenna not found, unknown, none. So this is the warning that you should pay attention to. It tells you the zero antenna applied instead. That means that you have no receive antenna information to be used. So there will be some confusion for this software. So the fixing rate is about 69.2%, right? This is for independent ambiguities. So this fixing rate is really low compared to some previous applications on the IGS stations. This is because the shaking of the airplane, the ambiguity fixing is not always so good to be done. So let's go to the 2020, and for the day 3 to 6. 3 to 6, we can see the KIN file is here. Let me see the KIN file for each epoch. So this is for 0.1 seconds. For each 0.1 second, we have one position here. And this is the satellite number. So we have 9 GPS satellites to be used by this airplane. So I'm not going to plot its. Okay, we can plot its track. We have a track. So track ROV9. So we can plot its track here to see how the airplane flies over the coast. So you see, this is the track for the horizontal plane, and this is for its height. So it stopped here and then flies to about 500 meters above sea level here, and then go down to the airport. So this is the track for the airplane. All right, so okay, we have 3 questions here. Let's see. Let me see. Hello? Okay, I can. Can you hear me?
Yes.
Okay, I changed my earphone because my earphone doesn't have any power now. All right, I have 2 questions about AR process. Are BeiDou geo satellites used for AR, and they are used for float solution only? For the geo satellites, they are used only for float solution. They're not used for ambiguity fixing. Because the geo satellites don't have precise orbits or clocks, and that will affect their ambiguity fixing rates. So we just exclude them from our ambiguity fixing process. They are used only for float solution, and their weights in the data processing are decreased by 9 times, as I have mentioned in the satellite list. You can see the numbers I put on behind them. After them, that's 3. So the code bias, induced bias are corrected with move. For the code bias, for satellite related code bias have been corrected for BeiDou 2. We use the model. We use the model released by a German scientist several years ago. It's just a table to correct for the
the biases caused by the beta 2 satellites. So you can so then you can do the ambiguity fixing for beta 2 satellites. All right, this is a good question for the station if not in the F mode. So in the F mode, if the station is not in the IGES station list, then you have to think about how to change the what kind of coordinates you want to put in your set XYZ file. So let me show you here for a few minutes. The troposphere estimation is quite direct using the configure daily file. So here we don't need to change. Actually, we don't need to change anything. We still use the AIRA station. So that station file is in the test data here. So we need to change it. And default, we use the WM products, and no changes here. We just use the file same. No changes here. So it's quite direct. The only thing you need to do is to change one thing here. ARA, okay, ARA 2020 0101, right? It should be on the first day. Oh, let me see. 001 ARA, yes, on the first day of 2020. So 2020 0101 and AIRA, we have for F and 30 seconds and Y. So I'm confusing. So here, normally we should use S or K for kinematic and S for static station estimate. But for the troposphere estimation, you have to use F. F means the station coordinates will be constrained tightly using the IGS solutions. So then we press it. We press the enter button and to start the processing. Here, you can see, right. Let's see. All right, this is the AIRA processing. So we have 3 constellations. It will be okay. Let me see this question. Does the software ignore in the system bias between biggest 2 over 10? No, it doesn't ignore. We do estimate in the system. We do not estimate in the system biases. We estimate 1 receiver clock for each system. So in the system biases are absorbed by the receiver clock of individual GNSS system. So you don't need to worry about the ISB. We do account for that. All right. I guess we have some professional GNSS scientists here. They know the details of GNSS data processing. All right, we see here, this is the ambiguity fixing. And then we come to 2020 and the 001, you see here. So this is the result for ARA for the troposphere estimation. We still have the position estimate because we need to constrain it. We still estimate the positions, but the positions are slightly constrained. So you can see here for the position mode, it's quasi-fixed station coordinates. But the uncertainty of these coordinates are very, very small. And these values are extracted from the IGS SANEX file. So it's about 1 millimeter uncertainty, 1 millimeter uncertainty. And these constraints are applied to your coordinates. And then we can produce a very precise estimate of troposphere. So now the troposphere is here, GTD file, and you can see the last 3 columns. This is dry component, and these 2 columns contains the wet component. This is the a priori correction for the wet component, and this is the estimation. This is the estimation, the estimate of the correction estimate for the wet component. So you have to combine them two to have a final estimate of your troposphere delay. So you can plot GTD using the plot GTD function ARA, and we have, this is the plot. This is the troposphere we estimated from using the ARA station here. So this is the station that we troposphere we estimated. So just ask the question about what if we don't have any coordinates reported from the IGS weekly solution? This is really a problem. Then you can manually resolve this problem by changing the content of the site XYZ file. You can see here, we have a site XYZ file here. This contains the coordinate information of that station. So you can open it, site XYZ, you can see for the AIRA station, we have the XYZ coordinates and this uncertainty here. If you can have the station coordinates from UNAVCO, I know UNAVCO is constantly processing their NOTA stations regularly. So they have their own daily position estimate. You can use that as well. But the software, this software cannot automatically refer to UNAVCO database to find those stations. So then you have to write a script, write a script in yourself to grab that coordinates to this site XYZ file to have this sigma information to be appended to the coordinates of the station, and then you can begin the troposphere estimation instead of the IGS weekly solutions. Yeah, the IGS weekly solutions do include very few stations around the world. It has only about 300 to 500 stations globally distributed. It doesn't include any station from NOTA or any other network station. So then you have to manually change or write a script to change the to extract that uncertainty information from other databases. All right, this is all for today, and we are approaching the final part. So this is I will upload these slides to you, so for your reference. Okay, let's come to, all right, you're welcome. So do you have any more questions on this? Let me upload these slides for you.
Hello, I have a
Yes.
small question.
Yes.
Yesterday I was practicing and I downloaded GPS data from the GNSS of Japan. I wanted to check the 2011 Toho earthquake event, and it didn't work. I couldn't download the
Okay.
the product.
Okay, you found it. You found the problem. Yeah, this is because we don't have, we haven't provided the product, the precise products for the year before 2020. It has only, we started to provide the latest the satellite products for the year of 2020 and 2021. We are doing the work to provide a complete list of satellite products for the past 2 decades, but that will take time. And in this case, you'd better use some other AC products, just as I have said. You can use COM products, you can use JPL products. You can use their products instead to process the data before the year of 2020. All right.
Okay.
Well, sorry for that. We are working on that. All right.
Okay. Thank you.
You're welcome. Let me try to. Someone said, do the satellite altitude cotillions have a meaningful effect on BDS only ER? Yes, of course. Satellite altitude cotillions, because if you don't use satellite cotillions, the satellites in the eclipsing seasons, because that kind of satellites cannot control the altitude precisely, and we actually don't know how the satellites change their attitudes in the eclipsing seasons. And in this case, if you use your own software, use some theoretical modeling algorithm to calculate the satellite attitudes in this case, that will cause some errors, and these errors will be absorbed by your satellite clocks. And that will increase your residuals of observations, and that will finally contaminate your ambiguities. So your ambiguity fixing may be impacted in an adverse way. So you have to think about attitude quotients. If this attitude quotient product are not provided by all ACs of IGS, so you can keep this part long if you are not going to use quotients. For example, here, daily. These 5 products are not required simultaneously. If you don't have quotients, you can just put long here, and then the software will not use any quotient products. And the software itself will use some theoretical modeling strategy to calculate the satellite attitudes in the eclipsing seasons. But that will cause some errors. Hopefully, this kind of errors will not be so huge, especially for GPS and the Galileo, which have better attitude control for the satellites in the space. But for Beidou satellites, especially for Beidou 2 satellites, the attitude control is not so mature over that period, and the attitude computation error will be huge for some satellites, for the GEO satellite, for the IGSO satellites. So that will cause some problem for your processing. More than one day. Yes, if you want to process more than one day of data, you need to have. Let me go to the processing directory. We have. Let me see. Control. Okay. Here we have this. Here we are processing one day data. But if you wanted to process more than one day data, for example, here 2 days of data to be connected together, you can change this session length to be a longer time. But in that case, you have to use GFZ Renex to combine the 2 Renex data together before you can process more than one data. I thought I planned to talk about this in this course, but finally I gave up because this is not a good way to process multiple data. We have the capability to do this, but this is not a good way because in that manner you have to change your Renex data. You have to use Jeff's Renex to combine 2 days data together, and that is not good for some users. So we are doing some modification here for the software to process multiple days of data without combining the Renex data together. We are teaching the software to recognize the multiple days of data one by one to have the process 1 day of data, and then it close that file and then open another Renex file to continually process the data. So, but at the moment you can combine them together to do multi-day data processing. Cutoff elevation and beacon option means is the mean elevation of the arc. Yeah, it means the mean elevation. It means the mean elevation of the arc, the mean elevation, because the ambiguity will span a few hours, right? At most, sometimes 6 hours for GPS satellites, and then this cutoff elevation means a mean elevation over that period. So if the mean elevation is lower than 15 degrees over the 6 hours or 5 hours or 4 hours, then that satellites will not be used for integer fixing. That satellites will be used for float solution, but not used for ambiguity fixing. So this is what's the name of the GFZ code to combine data? The orbit combination can be done by the software itself. If you put multiple days of orbits here, for example, you can, here we use only 1 day of orbits, but you can also put multiple days of data here, multiple days of orbits here. For example, you can use, this is 001, you can put 002 here as well. You can put as many days as you can here, and then the software will recognize this and combine the orbits together automatically for multi-day processing. So this is the trick to do that multi-day processing. All right. GFS Renix to combine. Yes, you have to use GFS Renix to combine the Renix data together as well. And this has to be done by the users themselves. The software will not automatically process multiple Renix file because that's a little bit that has not been coded in our software. You need to combine the Renix data together yourself. You are using GFS Renix at first, and then you can put multiple days of products here, clocks, orbits, and ERPs here, and then you can start to process multiple days of data. You will see a newer version in the near future to deal with this problem for multi-day processing. So without combining the Renix data together, you only needed to put the data, put the multiple days of Renix data in one directory, and then the software will recognize and process the data one by one to finish the multi-day data processing. But this is under the way. We haven't coded it. It needs to make some modification of the software. So hopefully we will do it in the near future. TAG can only process GPS and GLONASS data. TAG cannot process Galileo or Beidou data. So if you wanted to combine multiple days of Renix data together, you'd better use GFS Renix. GFS Renix is very powerful. It can process all kinds of constellations. So TAG is, I think TAG has been stopped, right? Has been stopped. So stopped updating. It can only process GPS and GLONASS. So it's not we're not using it anymore. Let me upload. Let me send you the send you. Okay, this is the slides. Okay, slides transferring here. Any more question here? TAG can handle all constellation, but only Renix 2, right? Really? Fred is reminding me of the of my thought. Right? Yes. I thought it can only process GPS and GLONASS, but all right. Okay, only Renix 2. Yes. GFS Renix can process Renix 3 as well. So so GFS Renix to be better used. And this is the Jonathan. Okay, good. So Jonathan has good information that he can run the Linux machine to run our software. So this is the final apology for the software that cannot be used in some Mac machines. Some Mac machines sometimes are really annoying. It's quite different from some Linux system. In China, we normally use a Linux system to do all of this work. So just in recent days, that's why we released version 2.1 too late for you, just a few hours before we start the courses, because we are doing the debugging for the Mac system. The Mac sometimes is quite annoying because it doesn't have so many. It is lack of so many tools and some grammar for work, and for B shell is also different from the Linux system. So it's really headache for us to do some adaptation for Mac system. So that will all right. Okay, and more question, Melissa? Do you so we can communicate further from using this Slack platform. So I will update you for some bugs in our software and also the latest version of the software. So we can still keep contact in this Slack platform. If you have any questions, and we can do some more communication on the problems. I would like to thank all of you guys, especially Jonathan and some other people. I forget the names, and you help us to fix some problems of the software, and we are looking for some incompatibilities of the software with some very special systems. And this is very important for us to make the software to be usable for as many users as possible. We wanted the common users to use this software to test our products, whether the products are of good quality. So if you find any problem for the products or the software, please do not hesitate to report it to us, and we can do some improvement for the algorithms or the script philosophy that can accommodate all kinds of very weird situations, right? All right. Okay, thank you for your feedback. Anyway, hey Melissa, shall we exit or close this session?
Yes, we can do that.
Thank you for your help, and thank you for your help. And this is a really great platform for us to communicate.
Yes.
I thank UNAVCO for providing me this opportunity to introduce our software. You know, it's not easy to make friends globally in some other ways, and I think this is one of the best ways for us to share our knowledge and to share our experiences with our colleagues in the world. Thank you, UNAVCO.
You're welcome.
All right. Okay.
Bye-bye.
Good. Bye-bye. See you guys.